In class, we've been working on transformations of random variables, and I want to do an example using the gamma distribution. And it might make sense for us to review the gamma distribution just in case you didn't use it too much in your probability prereq. It will be important for this course. Some distributions related to statistical estimators, for example, are related to the gamma distribution. So let's first write down the PDF of the gamma. So we'll denote it as f of x, and then we'll do distribution. We'll use alpha and beta for the parameters. And so we've got some constants out front, a 1 over the gamma function alpha. And if you don't remember what the gamma function is, I'll remind you in just a bit. Then we'll multiply by beta raised to the alpha and an x to the alpha minus 1, and then an e to the negative beta times x. And then we'll throw an indicator function at the end, the indicator over 0 to infinity of x. And so here we should note, this is for an alpha greater than 1 and a beta greater than 1. And then let's also say what the gamma function is. So the gamma function, it's a function of alpha, and it will be an integral from 0 to infinity. And we'll have to use some variable stand-in, so I'll use t. So it's an integral from 0 to infinity of t to the alpha minus 1 e to the minus t dt. So notice the integral is over t, right? You're integrating out those t's, and the gamma function is a function of alpha, which is a positive real number. And just take note that the gamma function, you can think of it as a generalization of factorial. So remember, factorial is a function that only works on non-negative integers, so 0, 1, 2, etc. But the gamma function holds for positive real numbers. And so you can think of it as a generalization, and we'll show one of the properties of the gamma function is that if you plug in an integer, a non-negative integer, so if you plug in an alpha that's equal to, say, 10, then you'll get 9 factorial. So in some sense, it's a generalization of the factorial. At every non-negative integer value, you get the factorial function, but it also evaluates for other real numbers, positive real numbers. But really, for our purposes in probability theory and statistics, the gamma function is really just the function that makes this PDF integrate to 1. So we really don't have to know too many properties about it once we get up and running and start using the gamma function. We just really note that if we integrate the PDF, right, over 0 to infinity, we should get 1. And if you integrated without the 1 over gamma of alpha, you would get something other than 1, but in fact you get the gamma function, and so that's why you need to divide by it. And we'll actually prove that fact now. So to show that 1 over gamma of alpha is the correct constant, we'll need to take the integral from 0 to infinity of beta to the alpha x to the alpha minus 1 e to the minus beta x dx, which is the green highlighted part just above. So if we take that integral and we get gamma of alpha, then we know that we have the correct constant, which would make our PDF integrate to 1. So the way that we'll do this is we'll combine some terms and then we'll do a u substitution. So let's group the beta times x together raised to the alpha minus 1. And so in doing that, we've changed the problem. We've raised beta to the alpha minus 1. So we've sort of thrown out a beta, and I'm going to put it back in the integrand here in just a second. So let's write out the e to the beta, negative beta times x. And then let's put that beta back in. So, now we have equality holding, right? We've sort of divided by a beta in one place and then multiplied by a beta in another place, and so that's just multiplying by 1. And the reason why we've done that is because now we can do a nice u substitution. So if we let u be equal to beta times x, then du is just beta dx. And if we make the substitution, the integral should be pretty easy. So the integral from 0 to infinity, here we'll have a u to the alpha minus 1, e to the negative u, and then du is left over because our du is beta times dx. So we've accounted for everything. And, well, look at that. This integral here is the same as the gamma function. And, the variable that we're integrating over is different, so it's a t in one place and a u in another, but of course that doesn't matter. That's just labeling. So this is gamma of alpha, right? And again, the alpha here corresponds to the alpha here. And so we've shown that this integral is equal to gamma of alpha, and that tells us that it's the right constant. So there are some other really useful properties of the gamma distribution and of the gamma function in particular. And so let's go over some of those properties because they'll be helpful in proofs that we do in this course. So the next property that we'll look at is the fact that gamma of 1 is equal to 1. And this is an easy proof. Right? We really just look at the integral from 0 to infinity of t raised to, so now here alpha is equal to 1, so it'll be 1 minus 1, and then e raised to the negative t dt. So of course that's the integral from 0 to infinity. So t raised to the 0 is just a 1, so this is just the integral of e to the minus t dt. And if you remember from your study of improper integrals, this integral is 1.